Hey, I've been diving deep into power electronics lately, and rectifiers keep coming up as a cornerstone. Can you break down the nuances of rectifier design and their real-world applications? I'm curious about how different configurations stack up.
Sure. Rectifiers are fascinating because they're the bridge between AC and DC worlds, critical for almost every electronic system. Let's start with the basics. A rectifier converts alternating current, which flips direction, into direct current, which flows one way. The simplest is the half-wave rectifier. Just a single diode that lets through either the positive or negative half of the AC cycle. But it's inefficient since it discards half the waveform. Full-wave rectifiers, like the center-tapped or bridge types, use both halves, giving you a smoother DC output. What's your take on where half-wave rectifiers still make sense today?
Honestly, half-wave rectifiers seem like a niche choice now. They're simple and cheap, so maybe in low-power, cost-sensitive stuff like basic battery chargers or small signal detectors in radios. But their ripple is so pronounced that you need hefty filtering to make the output usable. Bridge rectifiers, with 4 diodes, seem to dominate because they don't need a special transformer and give you double the output frequency, which eases filtering. Do you think the extra diodes in a bridge are always worth the cost and complexity?
Great point about the ripple. The bridge rectifier's higher output frequency, twice the input, means smaller, cheaper capacitors for smoothing, which is a big win in most designs. The extra diodes do add cost and a bit of voltage drop, about 1.4 volts total for silicon diodes. But in high-power applications, that's negligible compared to the benefits. Center-tapped full-wave rectifiers, though, need that special transformer, which can be bulky and expensive. I've seen them in vintage audio amps, where the transformer's already part of the design. But for modern compact systems, bridges rule. Let's talk real-world. Where have you seen rectifiers making a big impact?
One place that stands out is in renewable energy systems, like solar inverters. The rectifier stage in a photovoltaic system converts the AC from microinverters or string inverters into DC for battery storage or grid synchronization. Bridge rectifiers are everywhere here because efficiency matters, and you're dealing with high currents. Another cool example is in electric vehicle chargers. Level 2 chargers use full-wave rectification to convert household AC to the DC that charges the battery. I'm curious though, how do you see active rectifiers, like those using MOSFETs, changing the game compared to traditional diode-based ones?
Active rectifiers are a game changer, especially in high-efficiency systems like EV chargers or data center power supplies. Traditional diodes have a fixed voltage drop, say 0.7 volts per diode, which leads to power loss, especially at high currents. MOSFET-based active rectifiers, or synchronous rectifiers, use transistors that can be switched on and off to mimic diode behavior, but with a much lower voltage drop, sometimes as low as 0.1 volts. This cuts losses significantly, boosting efficiency to 95% or higher. The catch? They need precise control circuits, which add complexity and cost. In low-power devices, the extra circuitry might not be worth it. But in something like a Tesla charger pushing hundreds of amps, it's a no-brainer. What's a use case where you think active rectification might be overkill?
I'd say in small consumer electronics, like a phone charger outputting 5W. The power loss from diodes is minimal at low currents, and the cost of adding MOSFETs and control logic would outweigh the efficiency gains. Plus, simplicity matters for mass production. Speaking of efficiency, let's pivot to filtering after rectification. Capacitors are standard, but I've seen inductor capacitor, LC, filters in high-end power supplies. How do you decide what filtering approach to use post-rectification?
Filtering is where you really shape the DC output. A capacitor alone is the go-to for most designs because it's simple and smooths out the ripple by storing charge during peaks and releasing it during troughs. But in high-current or high-precision systems, like medical equipment or server power supplies, an LC filter can be better. The inductor resists rapid current changes, reducing ripple further, and the capacitor handles the high-frequency noise. The trade-off is size and cost. Inductors are bulky. I'd choose a capacitor-only filter for something like a laptop charger, but go LC for a high-power industrial system. Quick quiz. What's the main factor determining the size of the smoothing capacitor in a rectifier circuit?
Nice one. It's the ripple voltage you're willing to tolerate. The capacitor size depends on the load current, the rectifier's output frequency, and how much voltage variation the circuit can handle. Higher current or lower frequency, like in a half-wave rectifier, means a bigger capacitor to keep ripple low. Did I pass? Let me flip it. What's a common mistake engineers make when designing rectifier circuits for high-power applications?
You nailed it. For the mistake, I'd say underestimating thermal management. High-power rectifiers, especially diode-based ones, generate heat due to the voltage drop across diodes. Engineers sometimes skimp on heat sinks or airflow, leading to overheating and reduced lifespan. I've seen this in early EV charger designs where diodes failed prematurely. Active rectifiers help here too, since they run cooler. Let's explore another angle. How do you think rectifiers impact power quality in the grid, especially with the rise of renewables?
That's a juicy topic. Rectifiers, especially in large-scale systems like wind or solar farms, can introduce harmonics distortions in the grid's voltage and current waveforms. Diode-based rectifiers draw current in pulses, which creates harmonic currents that can mess with grid stability or interfere with other equipment. Active rectifiers with power factor correction, PFC circuits, are better because they draw smoother, sinusoidal currents, improving power quality. But they're pricier, so it's a trade-off. I've read that some utilities are pushing for stricter harmonic standards because of this. Have you seen any innovative solutions to mitigate rectifier-induced harmonics?
Absolutely. One cool approach is using multi-level rectifiers like 3-level or 5-level topologies in high-power systems. These spread the switching across multiple voltage levels, reducing harmonic content and improving efficiency. They're complex but showing up in grid-tied inverters for renewables. Another trick is active filters, dedicated circuits that inject counteracting currents to cancel harmonics. These are pricey but effective in data centers or industrial plants. Let's wrap with a challenge. If you were designing a rectifier for a 100 kilowatt solar inverter, would you go diode-based, active, or something else, and why?
For a 100 kilowatt solar inverter, I'd lean toward an active rectifier using IGBTs or MOSFETs with PFC. Efficiency is critical at that scale, and active rectifiers minimize losses while keeping harmonics low, which is a must for grid compliance. Diode-based would be too lossy and harmonic-heavy, even with filters. I might even consider a multi-level topology if cost allows, for extra efficiency and lower switching stress. What would you pick?
I'm with you on the active rectifier, but I'd push for a 3-level topology if the budget's there. It's overkill for smaller systems, but at 100 kilowatts, the reduced harmonics and stress on components justify it. Plus, it future-proofs the design for stricter grid codes. This was a great dive. Rectifiers are such a small piece, but have massive ripple effects. Pun intended.
Haha, nice pun. You're right, rectifiers are small but mighty. Let's pivot to another layer of rectifier design, the role of transient response, especially in dynamic systems. I've noticed that in applications like motor drives, the rectifier has to handle sudden load changes. How do you ensure stability in those scenarios?
Transient response is critical in dynamic systems like motor drives or variable frequency drives. When the load changes abruptly, say a motor starts or stops, the rectifier's output can sag or spike, messing with the DC bus voltage. A well-designed rectifier circuit needs a robust DC link capacitor to absorb those transients. The capacitor acts like a buffer, supplying or absorbing current to keep the voltage steady. But it's not just about size. The capacitor's equivalent series resistance, ESR, and inductance, ESL, matter too. Low ESR capacitors, like ceramics or film types, respond faster to transients. Have you come across any tricks for optimizing transient response without oversizing the capacitor?
Yeah, oversizing capacitors can balloon costs and size, which is a pain in compact designs. One trick I've seen is using a hybrid approach. Pair a smaller, high-quality capacitor with low ESR for fast transients with a larger electrolytic capacitor for bulk energy storage. This combo handles both quick spikes and longer-term load changes without breaking the bank. Another approach is active damping, using control circuits to adjust the rectifier's switching in real time to counteract transients. It's more complex but super effective in high-performance systems. What's your go-to strategy for balancing cost and performance here?
I like your hybrid capacitor idea. It's a practical middle ground. My go-to is similar, but leans on predictive control algorithms when using active rectifiers. By monitoring load current and predicting demand, you can adjust the switching to preempt transients. reducing the burden on capacitors. It's like giving the rectifier a brain to anticipate changes. For cost-sensitive designs, though, I stick to optimizing passive components and sometimes add a small inductor in the DC link to smooth current fluctuations. It's less elegant but gets the job done.
Quick quiz. What's a key factor that could degrade a rectifier's transient response in a motor drive?
Nice one. I'd say parasitic inductance in the DC link or wiring. It can cause voltage overshoots or ringing during fast load changes, destabilizing the system. Proper layout and minimizing loop inductance are critical. Did I get that right? Here's my question. In high-frequency applications, like RF power supplies, how do you deal with rectifier switching losses?
Spot on with parasitic inductance. For high-frequency applications, switching losses in rectifiers can be a killer, especially with traditional diodes. At RF frequencies, think MHz range, diode reverse recovery time becomes a bottleneck. Fast recovery or Schottky diodes are a must because they switch quicker and lose less energy. Even better, active rectifiers with wide bandgap devices like GaN or SiC transistors shine here. Their low switching losses and high-speed operation make them ideal for RF power supplies. The downside?
Cost and the need for precise gate drivers. I've seen GaN-based rectifiers in 5G base stations pushing efficiency past 98%. What's a high-frequency rectifier challenge you've run into?
In RF amplifiers, I've struggled with electromagnetic interference, EMI, from rectifier switching. Those fast transitions create noise that can couple into the RF signal, degrading performance. Shielding and careful PCB layout help, but I've also used snubber circuits to dampen switching transients. GaN devices do help, but as you said, the gate drive complexity is no joke. Let's shift gears to reliability. In harsh environments, like automotive or industrial settings, how do you ensure rectifiers keep performing?
Reliability in harsh environments is all about ruggedness. In automotive systems, rectifiers face extreme temperatures, vibrations, and voltage spikes. I'd use diodes or MOSFETs rated for wide temperature ranges, like automotive-grade components with AEC-Q 101 certification. Thermal management is huge. Heat sinks, thermal vias, or even liquid cooling for high-power setups. For industrial settings, like factory automation, you also need protection against voltage surges from grid fluctuations. Transient voltage suppressors, TVS, or varistors can clamp spikes.
One neat trick is using redundant rectifier stages in critical systems to ensure failover. Have you dealt with rectifier failures in the field? What was the root cause?
I saw a failure in an industrial welding system where the bridge rectifier diodes fried due to inadequate cooling. The design underestimated the heat from high current surges during welding cycles. Adding a beefier heatsink and switching to Schottky diodes fixed it. It taught me to always overspec components for worst-case scenarios. Speaking of worst case, how do you handle rectifier design for systems with unstable input, like portable generators or weak grids?
Unstable inputs are a nightmare. Portable generators often have noisy, fluctuating AC with varying frequency. A robust rectifier design starts with a wide input range topology. Active rectifiers with PFC are great here, because they can adapt to voltage and frequency swings. You'd also want input filtering, like EMI filters, to clean up the noise before it hits the rectifier. In weak grids, like in rural areas, voltage sags are common, so a boost stage post-rectification can stabilize the DC output. I've seen this in off-grid solar setups paired with generators. What's a real-world, unstable input scenario you've tackled?
I worked on a portable medical device powered by a small generator in remote clinics. The AC input was all over the place, voltage dips and frequency jitter. We used a bridge rectifier followed by a buck-boost converter to keep the DC output rock solid. Added an input filter to tame the noise too. It was a lifesaver for consistent operation. Let's zoom out. With the push for greener tech, how do you see rectifier design evolving over the next decade?
Green tech is driving rectifier design toward higher efficiency and smaller footprints. Wide bandgap devices like SiC and GaN will dominate because they cut losses and enable compact designs for things like EV chargers and renewable inverters. I also see smarter rectifiers with integrated sensors and AI-driven control to optimize efficiency in real time, especially in smart grids. Modular, scalable rectifier designs will be big too, allowing easy upgrades as power demands grow. Final quiz. Name one emerging technology that could disrupt traditional rectifier designs.
I'd say direct AC to DC conversion using matrix converters. They skip the traditional rectifier stage entirely, reducing components and losses. It's still niche but could shake things up in compact, high-efficiency systems. Your thoughts?
Matrix converters are intriguing. They're complex to control, but the potential for fewer stages and higher efficiency is huge, especially in space-constrained applications like aerospace. I think we're just scratching the surface of what's possible with power electronics. This was a blast. Rectifiers may seem basic, but they're the unsung heroes of modern electronics.
Hey, I've been brushing up on electronics basics, and capacitors keep popping up everywhere. They seem simple, but also kind of magical. Can you walk me through how they actually work? Maybe with some real-world context to make it stick?
Love the enthusiasm. Capacitors are like tiny energy buckets, and they're anything but boring. At their core, they store electrical energy in an electric field between two conductive plates, separated by a non-conductive material called a dielectric. When you apply voltage, one plate gets a negative charge, the other positive, and the dielectric keeps them from shorting out. The magic happens in how they charge, discharge, and interact with circuits. Want me to start with the charging process or jump to a cool application first?
Let's start with the charging process. I've heard capacitors fill up with charge, but I'm fuzzy on the details. How does that work? And why doesn't the current just keep flowing forever?
Great question. Imagine a capacitor as a small water tank with a narrow pipe. When you connect it to a voltage source like a battery, electrons rush onto one plate, making it negative, while the other plate loses electrons, becoming positive. This creates an electric field across the dielectric. At first, the current is high, because the capacitor is empty, but as it fills with charge, the voltage across the plates builds up, opposing the source voltage. When the capacitor's voltage equals the source's, current stops. Think of the tank being full, so no more water can flow in. The dielectric's key here. It boosts how much charge the capacitor can hold. Ever wonder why some capacitors are bigger than others for the same job?
I'd guess size has to do with capacitance, right? Bigger capacitors can store more charge, maybe because of larger plates or a better dielectric. But what makes a dielectric better? And does the size always matter in real circuits?
You're on the right track. Capacitance, measured in farads, depends on three things: the plate area, the distance between plates, and the dielectric's permittivity. Basically, how well it can polarize to enhance the electric field. A better dielectric, like ceramic or tantalum, has higher permittivity, letting the capacitor store more charge in less space. Size matters, but it's not just physical. Different dielectrics suit different jobs. For example, electrolytic capacitors are big and great for power supplies because they offer high capacitance, but they're slow and can't handle high frequencies. Ceramic ones are tiny and fast, perfect for signal filtering. Real-world example. In a camera flash, a big electrolytic capacitor stores the energy for that bright burst. Quick quiz. Why do you think a capacitor blocks DC but lets AC pass?
Ooh, good one. I think it's because DC is steady, so once the capacitor charges up, it acts like an open circuit. No more current flows. But AC keeps changing, so the capacitor's constantly charging and discharging, letting current pass. Nailed it? Here's my question. In a power supply, how does a capacitor smooth out the bumpy DC from a rectifier?
You nailed it. That's exactly why capacitors block DC and pass AC. Now, for your power supply question. After a rectifier converts AC to DC, the output is pulsating like a series of hills, especially with a half-wave rectifier. A capacitor acts like a reservoir. When the rectifier's output voltage peaks, the capacitor charges up, storing energy. When the voltage dips between pulses, the capacitor discharges, supplying current to keep the voltage more stable. The bigger the capacitor, the smoother the output. But you also need to balance size and cost. In a laptop charger, you'll see this smoothing in action, keeping the DC steady for the electronics. Ever notice how some cheap chargers make devices hum? That's often a skimpy capacitor. What's another capacitor application you've come across?
That humming makes sense now. I've seen capacitors in audio gear, like guitar amps, where they seem to separate signals between stages. I think it's called coupling. Can you explain how that works and why capacitors are used instead of, say, a direct wire?
Spot on with coupling. In audio amps, coupling capacitors are used to pass AC signals, like the music waveform, between circuit stages while blocking DC. Each stage of an amplifier often has a DC bias to set the operating point of transistors or tubes. If you used a wire, that DC would mess up the next stage's bias, causing distortion or even damage. A capacitor lets the AC signal ride through because it responds to voltage changes, but it blocks the steady DC. In a guitar amp, this ensures the clean audio signal moves from the preamp to the power amp without carrying unwanted DC. The capacitor's value matters too. Too small, and it cuts low frequencies, thinning out the bass. Have you ever tinkered with an audio circuit and noticed a capacitor's impact?
Not yet, but that's super clear. I'm picturing the capacitor as a gatekeeper, letting the music through but stopping the DC noise. I've also heard about capacitors in timing circuits, like in blinkers or timers. How do they control timing, and what's the trick to picking the right capacitor for that?
Timing circuits are a classic capacitor use case. The trick lies in the capacitor's charging and discharging speed, which depends on its capacitance and the resistance in the circuit. Together, they form an RC circuit with a time constant, tau, which sets how fast the capacitor charges or discharges. In a blinker circuit, like for a car's turn signal, the capacitor charges through a resistor until it hits a threshold, triggering a switch, like a transistor or IC, to discharge it, creating a pulse. This repeats, making the light blink. Picking the right capacitor means calculating the capacitance to match your desired timing interval. For example, a 10 microfarads capacitor with a 10 kilo ohms resistor gives a time constant of 0.1 seconds. Good for a slow blink. Too big a capacitor, and the blink's too slow. Too small, and it's too fast. Ever played with a 555 timer chip? It's a capacitor timing superstar.
I've heard of the 555 timer but haven't tried it yet. Sounds fun. That timing explanation clicks though. It's like the capacitor's pacing the circuit. Let's talk failures. What happens when a capacitor goes bad, and how do you spot it in something like a power supply?
Capacitor failures can wreak havoc. In a power supply, a bad capacitor, often an electrolytic one, might leak, bulge, or lose capacitance due to age, heat, or overvoltage. Symptoms include excessive ripple, so the output voltage isn't smooth, causing devices to glitch or hum. You might spot a bulging capacitor visually or feel it's hot. A multimeter can test capacitance, but in circuit, an oscilloscope showing ripple is a dead giveaway. In old TVs, a failed capacitor could cause flickering or no power. Replacing it often fixes the issue, but you need the right type and rating. Quiz time. What's a common cause of capacitor failure in high-temperature environments?
I'd say heat, drying out the electrolyte in electrolytic capacitors, reducing their capacitance, or causing leaks. Right? My turn. In a touchscreen, how do capacitors play a role in sensing touch?
Exactly right. Heat is a killer for electrolytics. For touchscreens, capacitive sensing is the star. The screen has a grid of tiny capacitors formed by conductive layers. Your finger, being conductive, changes the capacitance at the point you touch by altering the electric field. The controller detects these tiny changes and maps your touch location. It's super sensitive, which is why gloves often don't work. Compare that to resistive touchscreens, which rely on pressure. Capacitive is smoother and supports multi-touch. Ever wonder how capacitor choice affects touchscreen performance?
That's wild. My finger's basically tweaking a capacitor. I'd guess the capacitor's dielectric and size affect sensitivity and response time. Thin, high-permittivity dielectrics probably make it more responsive. Let's wrap with the future. How are capacitors evolving for things like electric vehicles or 5G?
You're spot on about dielectrics. For EVs and 5Gs, capacitors are getting smaller, tougher, and more efficient. In EVs, high capacitance, high voltage capacitors stabilize power in inverters and store energy for regenerative braking. New ceramic and film capacitors handle extreme temperatures and high frequencies better than old electrolytics. For 5G, tiny, high-frequency capacitors filter signals in base stations and phones, ensuring clean data transfer. Research into graphene and other nanomaterials promises even higher capacitance in smaller packages. Capacitors may be simple, but they're evolving fast to keep up with tech. This was a blast.
Ready to build a 555 timer circuit yet?
Hey, I've been digging into transistors lately, and they're blowing my mind. Such tiny things powering everything from phones to rockets. Can you break down how they actually work, especially the difference between BJTs and MOSFETs? I want to get a feel for their real-world roles.
Transistors are the unsung heroes of electronics, no doubt. At their core, they're semiconductor devices that either amplify signals or act as switches by controlling current flows. BJTs and MOSFETs are the big players, and they're quite different beasts. A BJT uses a small current at its base to control a larger current between its collector and emitter. Think of it like a valve tweaking a big water flow with a small nudge. MOSFETs, on the other hand, use a voltage at the gate to control current through a channel, more like flipping a switch with an electric field. Want me to start with BJTs or MOSFETs to unpack their mechanics?
Let's start with BJTs. I've heard they're great for amplifiers, but I'm fuzzy on how a tiny base current can control so much power. Can you explain that and maybe give a real-world example?
Sure thing. A BJT, or bipolar junction transistor, has three parts: emitter, base, and collector. In an NPN BJT, you apply a small positive voltage to the base, which lets a tiny current flow into it. This current unlocks the path between the emitter and collector, allowing a much larger current to flow through. The magic is in the current gain called beta, which can be 20 to 1000. So, a microamp of base current might control milliamps, or amps of collector current. In real life, think of an audio amplifier in a guitar amp. A weak signal from the guitar hits the bass, and the BJT boosts it to drive a speaker, filling a room with sound. Ever wonder why BJTs aren't used everywhere, given that amplification power?
That's a great analogy. I'm guessing BJTs aren't universal because of power or speed issues? I've heard MOSFETs are faster and more efficient, especially in digital stuff. How do they work differently, and why are they so popular in things like CPUs?
You're right on the money. MOSFETs, metal oxide semiconductor field effect transistors, are the darlings of digital circuits. Unlike BJTs, which need current to control current, MOSFETs use a voltage applied to a gate electrode. This gate is insulated by a thin oxide layer, so it draws almost no current, making MOSFETs super power efficient. The gate voltage creates an electric field that forms a conductive channel between the source and drain, letting current flow. In a CPU, millions of MOSFETs act as switches on or off for binary logic. They're fast because they switch in nanoseconds and efficient since they don't waste power on gate current. Think of a modern processor like in your phone. MOSFETs enable billions of calculations per second while sipping battery power. Quick quiz. What's a key advantage of MOSFETs over BJTs in digital circuits?
I'd say it's their high input impedance, so they don't draw much current at the gate, saving power. Did I get that? Here's my question. In something like a power supply, how do you decide whether to use a BJT or a MOSFET?
Nailed it. High input impedance is a huge win for MOSFETs. For power supplies, the choice depends on the job. BJTs are great for linear power supplies, where you need smooth, precise voltage regulation. Like in high-end audio equipment, they're linear, so they produce less noise, but they're less efficient, generating heat. MOSFETs shine in switching power supplies, like in laptops or EV chargers, because they switch fast and lose less power as heat. Their low on resistance and high efficiency make them ideal for high-frequency switching, which shrinks transformer size. If I'm designing a compact, high-power charger, I'd pick MOSFETs. Ever worked on a circuit where transistor choice made a big difference?
Not hands-on, but I read about a motor controller where switching from BJTs to MOSFETs cut power losses by half, making the system cooler and more efficient. That got me thinking about high-power stuff. I've heard about IGBTs in electric vehicles. How do they fit into the transistor family?
Great example. IGBTs, or insulated gate bipolar transistors, are like a hybrid of BJTs and MOSFETs, blending the best of both. They've got a MOSFET-like gate, so you control them with voltage, not current, making them efficient. But their output stage works like a BJT, handling high currents and voltages, think hundreds of volts and amps. In electric vehicles, IGBTs are the muscle in inverters, converting battery DC to AC to drive the motor. They can handle the massive power demands while switching fast enough for efficiency. Downside? They're not as fast as MOSFETs, so they're less common in super high-frequency circuits.
Ever wonder how transistor choice affects something like renewable energy systems?
Yeah, I've been curious about solar inverters. I assume MOSFETs or IGBTs are used to handle the high power, but how do they deal with the variable input from solar panels? And what's a challenge you face in those designs?
Solar inverters are a perfect case. They typically use IGBTs for high-power stages, like converting DC from panels to AC for the grid. Because IGBTs handle high voltages well, MOSFETs might be used in lower power or high-frequency stages, like MPPT, maximum power point tracking, circuits, which adjust to the panel's varying output due to sunlight changes. A big challenge is efficiency under partial load. Solar output fluctuates, so the inverter needs to stay efficient across a wide range. Another issue is thermal management. High-power transistors generate heat, and poor cooling can kill reliability. Advanced designs use wide bandgap materials like SiC or GaN for better efficiency and heat tolerance. Quiz time. What's a common failure mode for transistors in high-power inverters?
I'd guess overheating, especially if the cooling system can't handle the heat from high currents or switching losses. Right? My turn. How do transistors in digital circuits, like in a CPU, keep getting smaller without breaking down?
Spot on. Overheating is a killer in inverters. For CPU transistors, shrinking them is the heart of Moore's law. We're down to 3 nanometers nodes now, using MOSFETs with FinFET structures, 3D designs that give the gate better control over the channel, reducing leakage. High-count dielectrics, like hafnium oxide, replace silicon dioxide to prevent electrons from tunneling through ultra-thin gates. Extreme ultraviolet lithography carves these tiny features. Challenges? Heat density is huge, and quantum effects like tunneling start messing things up. New materials like graphene or 2D semiconductors are being explored to keep scaling. Have you heard about any cutting-edge transistor tech?
I read about carbon nanotube transistors, supposedly super fast and efficient. They sound promising but tricky to manufacture. Let's talk reliability. What's a common mistake engineers make when designing with transistors?
Carbon nanotubes are exciting, but yeah, a manufacturing nightmare for now. A common design mistake is improper biasing. For BJTs, if the base voltage or current isn't set right, you might push it into saturation or cutoff when you want amplification, ruining performance. For MOSFETs, not accounting for gate drive voltage or capacitance can lead to slow switching or even damage from static discharge. I've seen circuits fail because engineers skipped thermal degrading, pushing transistors too hard without enough cooling. Real-world example. A poorly biased BJT in an audio amp can clip the signal, making music sound awful. What's a transistor circuit you'd love to design?
I'd love to try a simple audio amplifier with a BJT, something to boost a microphone signal for a small speaker. Sounds like a fun way to learn biasing. Let's wrap with the future. How do you see transistors evolving for things like quantum computing or AI hardware?
An audio amp's a great project. BJTs are perfect for that. For the future, transistors are heading towards specialized roles. In quantum computing, we're seeing superconducting transistors, or spin-based transistors for qubits, operating at cryogenic temperatures. For AI hardware, like neural network accelerators, low-power, high-density MOSFETs are key, but we're also seeing analog transistors for in-memory computing to cut energy use. Wide bandgap materials like GaN and SiC will keep pushing efficiency in power-hungry AI servers. Transistors are evolving to meet crazy new demands, and it's exciting to see where they'll go next. Ready to breadboard that amp yet?